This is Math 105, section 7.1. In this section, we'll be looking at some trig identities and proving some of them and looking at ways to do that. So let's start with kind of our basic reciprocal identities that we already talked about. Remember, cosecant is 1 over sine. Secant is 1 over cosine. Cotangent is 1 over tangent. Tangent is sine over cosine, and cotangent is cosine over sine. So we know those already. And we also know that sine squared plus cosine squared is 1. If we divide both sides by cosine squared, we get tangent squared plus 1 equals secant squared. If we divide both sides by sine squared, we get 1 plus cotangent squared equals cosecant squared. And you can kind of remember those that the cos go together, cotangent, cosecant. If we add 1 to cotangent squared, we get cosecant squared. And then the tangent, the non-cos, tangent and secant go together. So tangent squared plus 1 is secant squared. Okay? Remember, sine is odd, so sine of minus x is minus sine of plus x. And the same with tangent. Tangent of minus x is minus tangent of plus x. But remember, cosine is even. Cosine of minus x is cosine of plus x. Okay, and then we haven't really looked at these in depth yet, but the cofunction identities. Now, it's done in this fashion with the pi over 2 first and then the angle because it applies to the cofunction. So if I go from sine to cosine or cosine to sine or tangent to cotangent or cotangent to tangent, or secant to cosecant or cosecant to secant, see, these are the cofunctions. It's kind of like its counterpart. Okay, but whenever you take sine of pi over 2 minus the angle, you get cosine of the angle. And same with cosine. Whenever you get cosine of pi over 2 minus the angle, you get sine. Okay, and that works with tangent as well. So if you go from tangent to cotangent, you can take tangent of pi over 2 minus the angle equals cotangent of the angle, angle being u. Okay, and then we can do the same thing with cotangent. So cotangent of pi over 2 minus u equals tangent of u. And we could also say 90 here as well, right? So, and then from secant to cosecant, same deal. So secant of pi over 2 minus u equals cosecant of u. And then cosecant of pi over 2 minus u equals secant of u. So, we put it in this order because we can see how it relates to its cofunction, okay? And it goes, it goes in reverse too, from sine to cosine and from cosine to sine, etc. So these cofunction identities will be useful when we're doing some, proving some trig identities, or trying to simplify things. Because if we have something like this, we can change it to cosine. Okay, now we're talking about simplifying trig expressions. So we use these identities, and they allow us we can write the same expression in different ways. Okay, so we can rewrite a complicated looking expression as a much simpler one, usually, which is what we're trying to do. And remember, we simplified algebraic expressions. We used factoring, common denominators, and the special product formulas that we had before, like difference of squares, difference of cubes, sum of cubes. For simplifying trigonometric expressions, we'll use these same techniques, okay, plus the fundamental trig identities that we just looked at. Okay, so kind of similar stuff we've been doing, but now we're going to use these trig identities too. Okay, so let's look at an expression example to simplify. Cosine of t plus tangent of t sine of t. Okay, so we know that tangent is sine over cosine, so we would substitute tangent of t for sine of t over cosine of t. Okay, and then now we want a common denominator here, right? So this is sine squared of t over cosine of t, if we multiply that out. So put this as cosine squared over cosine, instead of cosine. So now we have a common denominator of cosine of t. So this becomes cosine squared over cosine. And remember, cosine squared plus sine squared is 1. So that's just 1 over cosine of t, or we can write it as secant of t. Okay, so this just becomes secant of t, or 1 over cosine. And we simplify that. Okay, now our next part, we're going to prove trig identities. Okay, so we have many identities that follow from our fundamental identities that we looked at. Okay, so now we're going to learn how to prove that a trig equation is an identity. In other words, that it's always true. Okay, so it's easy to decide when it is not identity. So it's easy to decide when a given equation is not an identity. We just show that the equation does not hold for some value of the variable. Okay, so when we want to prove that it's not an identity, or if we get an example where it's not true, then we know it's not an identity, because remember, identity is always true. Okay, so if we find a case where it doesn't work, then we're done. We can say it's not true. Okay, so for example, sine of x plus cosine x equals 1 is not an identity. It's not always true because look at what happens when x is pi over 4 as a simple example. We have sine of pi over 4 plus cosine of pi over 4 is square root of 2 over 2 plus square root of 2 over 2, which is square root of 2, right? This is 1/2 of square root of 2. There's another half of square root of 2, which gives us 1 times square root of 2. Not equal to 1, okay? So that is not an identity, okay? Now, if we want to verify that a trig equation that actually is an identity, in this case we don't, it's not an issue, we transform one side of the equation into the other side by a series of steps, okay? So basically we're going to work on one side and try to get equal to the other side. And once we do that, we've shown that it's an identity, okay? And we're usually going to start with the more complicated side and try and simplify it to get to look like the less complicated side. Okay, so here's our steps. So guidelines for proving trig identities. Start with one side. Pick one side of the equation and write it down. Your goal is to transform it into the other side. Okay. Usually easier to start with the more complicated side to do that with. Okay. So we take the more complicated side and try to make it simpler to look like the other one, the other side. Use our known identities that we talked about. Okay, so change the side. Use these identities to change the side you started with. Okay. Make sure we use fractional expressions, bring them to a common denominator, factor, and use fundamental identities to simplify. So we're going to use the identities that we looked at in the first slide to simplify. Okay. Convert to sines and cosines. That's a good rule of thumb too. Generally, we're going to try to put everything in terms of sine and cosine. So if you're stuck, you might find it helpful to rewrite these functions in terms of sine and cosine. So we have, just those two functions. Sometimes not, but for the most part, that works. Okay, let's look at this expression. Cosine of theta times secant of theta minus cosine of theta, in parentheses, equals sine squared. Okay. First of all, we want to verify that it's an identity and confirm that graphically. Okay, so let's do the left-hand side because it looks more complicated. So change this to 1 over cosine, secant. So we're using everything in sine and cosine. And then we have cosine of theta times 1 over cosine minus cosine. Okay, using the reciprocal identity there. Okay. And when we distribute cosine of theta on this, we get cosine of theta times 1 over cosine of theta is 1, and this will be cosine squared of theta. So we get 1 minus cosine squared of theta. Okay, so when we do the distribution, we got 1 minus cosine squared of theta, which is equal to sine squared of theta, because remember sine squared plus cosine squared is 1, right? So now we got our right-hand side, right? So which is sine squared. So we've proven this identity because we simplified the left-hand side and we got sine squared, which is equal to our right-hand side. We're not going to worry about graphing the identity to prove it, so don't worry about that. We'll just do the algebraic stuff here. Okay, the next example we'll look at, we're trying to verify this identity. U is our angle. Cosine of u over 1 minus sine of u equals secant of u plus tangent of u. Okay. Now we can make this into sine and cosine. This would be 1 over cosine plus sine over cosine. But let's worry about this side first. Okay. Whenever you have like a 1 minus sine or 1 minus cosine or 1 plus sine or 1 plus cosine, you can actually turn it into just a single trig function, like without the 1. We could turn this into cosine squared. Here's what you can do. Take your 1 minus sine of u and multiply it times 1 plus sine of u. Think of that like a conjugate, right? Remember, difference of squares is, let me write that as a square there. Okay. Difference of squares is a minus b times a plus b, right? So if you take the conjugate of this and multiply it, you're going to get 1 squared minus sine squared, which is 1 minus sine squared, which is cosine squared. So if you multiply this times 1 plus sine of u, you just get cosine squared. And then that also works for cosine. So let's say we have 1 minus cosine of u. If we multiply times 1 plus cosine of u, we would get 1 squared minus cosine squared of u, which is sine squared. Okay. So it's the same idea. If you multiply this times its conjugate, you're going to get rid of that 1 plus or 1 minus. Okay. So if you have a 1 plus sign, you can multiply times 1 minus sign, and you're going to get cosine squared. If you have a 1 plus cosine, you can multiply times 1 minus cosine, and you get sine squared. Okay. So let's do that here, because we want to get rid of this denominator here, or at least simplify it. Okay. So we take the side, and we multiply it times 1 plus sine of u, the conjugate of that denominator, and we do the same thing on the top, right? Okay, so think of that like a conjugate, just like we did for rational numbers for irrational numbers, we're rationalizing our denominator, and just like we did for complex numbers with I, right? So think of it like a conjugate thing, and again, we're using difference of squares. A minus b times a plus b is a squared minus b squared, okay, which in this case gives us cosine squared. Okay, so on the bottom we took 1 minus sign times 1 plus sign gives us 1 minus sign squared, difference of squares, and we haven't done the multiplication on the top yet. Okay, but this gives us cosine squared. 1 minus sine squared is cosine squared. Okay, and then once we do this, we have cosine cancels out, right? We divide by cosine here, and we divide by cosine here. We just get a 1, right? So that would give me 1 plus sine of u over cosine of u. Okay. And then we can break out the fraction to be 1 over cosine of u plus sine over cosine, right? If we take this out separately, okay, and that's equal to secant plus tangent, right? Secant is 1 over cosine, and tangent is sine over cosine. So we've proven the identity by saying, yeah, look, we simplified this, and we got this, which is secant, and this, which is tangent, which is what we had on the other side. Okay, so that's how we prove that identity algebraically. Okay. Maybe both sides are kind of complicated. Maybe one's not easier to pick than the other. If we can transform each side of the equation separately using identities to arrive at the same result, then the equation is an identity. So we may have to work with both sides and get them simplified where they're both equal. Okay, so maybe both sides are a little bit complicated. We might have to work on both. So that's a possibility. So let's look at this example. We have 1 plus cosine of theta over cosine of theta, and we want to make sure that that's equal to tangent squared over secant of theta minus 1. Okay, so let's do the left-hand side first. Okay, 1 plus cosine of theta is 1 over cosine of theta plus cosine over cosine, because we break out that fraction, right? 1 over this plus 1 over cosine of theta plus cosine of theta over cosine, which is, now this is secant plus 1. Okay. All right, that looks pretty, like a pretty simplified form. It's not sine and cosine, but that's okay. Remember I said sometimes we don't want to use just sine and cosine. Sometimes we just want to simplify and then compare. Okay, so we have secant of theta minus 1 for the left-hand side. That's what LHS stands for. Okay, now let's do the right-hand side. Okay, we kind of did a trick with the right-hand side. Remember from one of our identities that tangent squared plus 1 is secant squared, right? So tangent squared is secant squared minus 1. Okay, if we move the 1 to the other side, subtract 1 on both sides, we'll get tangent squared equals secant squared plus 1. So our right-hand side, RHS, started with this. We're going to change tangent squared to secant squared minus 1. Okay, we still have secant minus 1 in the denominator. Okay, but recognize that this is a difference of squares, right? This is secant squared minus 1 squared. So we can write it as a minus b times a plus b, or in other words, secant minus 1 times secant plus 1, right? Difference of squares. Okay, and then what happens then? Well, this cancels out, right? The denominator and this cancel out, right? Which gives us secant plus 1. Okay, and that's what we got on the left-hand side. So we've shown that it's identity because we got secant of theta plus 1 on both sides. Okay, so this is a case where we had to simplify both sides to prove that identity.